Um, my name is Norbert, and the topic of the day, for me at least, is nonlinear simulations of complex memory-affected RF circuits. Thank you, of course, for the kind introduction and the option of presenting this topic here. And in my academic career, I actually learned one thing by heart. This is not to get in the way between an engineer and his lunch. So I really would try my very best to keep the time schedule ahead of us. First of all, I want to give a brief introduction about this overall topic. Then I will carry on with a glimpse at the all-digital RF transmitter, which my colleague Bernhard Bichler already kindly introduced, so we can save some time on that. Then I will carry on with the lookup table model, which is actually the one element that does the trick with simulating this kind of circuits in an efficient manner. Then I will carry on with the nitty-gritties of how to plug that into microwave office. And in the end, I will show how this can be incorporated into a MATLAB-based optimization run, which is, I guess, one of the most interesting things for the people here. So we'll try to spend some time on that. Okay then, first of all, I want to present a bit of a motivation why we are currently looking into this kind of somehow exotic circuits. So first of all, new modulation formats and new telecommunication standards have been put out hastily somewhat, and we try to meet all these criterions, even they are sometimes kind of tricky. So we're looking for very power efficient operation because we want to have long battery life or low costs with regards to supplying the energy to that. We want to have it reconfigurable with respect to center frequencies, bandwidths, modulation schemes. We want to have potential high linearity, and on the other hand, by developing circuits that can do all that, which is, for example, the class of all digital RF transmitters, we throw overboard some very proven through basic circuit design concepts, like we, for example, entangling the modulator and the amplifier itself, and on the other hand, some traditional distortion measures and therefore also circuit design concepts need to be replaced. And to walk you through one of these kind of exotic birds of all digital RF transmitters, I want to present this chart, where on the left side here you can see we have a modulator, which is basically a piece of software which takes in baseband data and performs a lot of fancy calculus and results in a very high rate stream of binary symbols, which is then played back using a very high speed single bit DAC, and you end up with a binary waveform which in the center actually reassembles the desired RF signal we want to have for our whatever system it is. And since this is basically a constant envelope signal, since it's binary nonetheless, we at least in theory could amplify it very power efficiently using switched mode power amplifiers in order to have a power efficient system. However, as a kind of a additional feature, we not only get an amplified signal, we also get nonlinear distortion, which is indicated by the spurs here in the signal. And of course, we are only interested in the center portion of the signal, and all the other modulator noise is basically a thing we want to get rid of. And therefore, we need a kind of reconstruction filter which eliminates these components. And since my colleague already introduced it a bit, this filter has to be highly reflective in order for the overall circuit to act energy efficiently. And this makes up for a very interesting design criterion. And at the end, of course, we would like to have this desired output signal, which is not so easy to achieve. And in order to study this, which is very interesting from an academic viewpoint, we came up with this basic lab setup that works as an all-digital RF transmitter, where we can see here at the bottom stage, this is the you may want to call it the output of the 1-bit DAC, which is basically a pulse driving amplifier from Triquant. I've already seen some Triquant name tags here today, so friendly shout out for the people of this company. And then the signal is supplied to the power amplification stage, which uses the 10 watt Cree hemp device everybody uses for building this kind of amplifiers. And then here at the end you get the glimpse of the reconstruction filter and the matching network, where we already had the presentation today on how to build this kind of fancy matching networks. So in a nutshell, this is the circuit, and now I want to present to you how we can use traditional state-of-the-art, I should say, circuit simulations in order to tackle simulation issues related to the circuits. And in order to do so, I first want to throw some numbers at you to give you an idea in which ballpark we are in with the circuit. So we are operating at very high bit rates. So the DAC is putting out 10 gigabits per second. The modulator considers a bandwidth of 833 megahertz of bandwidth in order to form this spectrum. It's basically a delta sigma PWM modulator, and we use a switched mode power amplifier which consists of these two active devices, one from Trico and one from Cree. And the target system for this project was a 20 megahertz LTE system. And since my colleague already introduced this chart, I just want to briefly sum up. So as you can see here, the output spectrum of the DAC is very densely populated. So there is some energy-rich components all over the place, and we are just really interested into this LTE signal here in the very center. So we need a very selective reconstruction filter that is, on the other hand, also highly reflective in its stop band. So we went with a custom-built fourth-order interdigital filter, where you can see here the transmission curve. And this one was matched to the overall circuit using the earlier presented simplified real frequency technique. If you're interested in how we went about that, I've stated the paper related to that here at the bottom. So if you're really interested, you of course can look it up. Okay then, when it now comes to this concept of the all digital RF transmitter with respect to dealing with the circuit on a simulation base, we can see that there are some practical issues. First of all, we need to conduct nonlinear simulations since we are pushing the switched mode power amplifier deep into saturation. And of course, we need nonlinear simulations to tackle that. On the other hand, the modulation sequence in order to depict one of these LTE frames is very lengthy. We're talking here now millions of bits. And of course, we need to operate on a certain oversampling rate in order to capture the form of the pulses. So this makes for very many sampling points. And on the other hand, the reflective output filter, which needs to have a high Q in order to be very selective, causes some memory effects in the circuit, which are a somewhat tricky thing to handle. Of course, filter models could be an approach to do so. On the other hand, we're just shifting the problem from solving the circuit simulations to identifying the proper filter model. So that's not really solving the problem. It's just pain conservation. And as my colleague already demonstrated, for building a really good design for such an all-digital RF transmitter, we need the statistics of the symbols and the excitation sequence, so we cannot oversimplify this kind of components. And the idea is now to have a twofold approach, which is called the lookup table model. And this is what I want to address in the next few slides. Just have a glimpse at the time. So the basic idea is that when I'm playing back a binary sequence and I'm just looking at the output waveform of the DAC, and since the modulator composes all of its output sequences from a very limited set of symbols, which is always a group of bits, we can see that, for example, this group of bits will always relate to such a sub-waveform in the overall output waveform, and we can relate this one-to-one. This, of course, only works if there is no memory effects present in the circuit. The moment we are here at the amplifier, in between the amplifier, between the reflective filter and the amplifier, actual load modulation causes precursory symbols to affect the current symbol. So a kind of nonlinear affected delay is introduced, which breaks this one-to-one relationship. On the other hand, and this is the good news actually, we still can address one of the sub-waveforms having a much longer, considering a much longer excitation sequence in terms of the symbols. And again, there is a paper for that. So if you're very interested in the nitty-gritties of these kind of things, you are invited to look it up. But I really don't want to get too nerdy on this subject here in this presentation. And the interesting thing now, to sum up, the circuit exhibits memory effects. The broadband excitation that has this very lengthy excitation sequence spoils classical harmonical concepts, since we would nearly have an infinite number of components we have to consider, and therefore it's not directly suitable for nonlinear circuit simulation. On the other hand, an interesting aspect is that we can group this excitation sequence in subsequences that are just long enough to capture the typical memory effects present in the circuit. And as long these groups of symbols is, speaking in terms of time, is longer than the effective memory effects that are present in the circuit, they are now accessible for state-of-the-art nonlinear circuit simulation in microwave office, for example. And this is actually what we went about to do. So we're using the modulator sequence, grouping it into groups of subsymbols, and using these ones to excite a nonlinear circuit model of this amplifier, including the nonlinear transistor model of Cree, a measured version of the filter and the matching network, and then we extract subwaveforms from that and storing them in a table. And then we can look that up and form our output waveform for a specific excitation sequence. And the good news is this works very well. We actually were able to show that by doing so we could predict the output waveforms. There are also some interesting aspects to that, how you can test it and how you can find, in fact, these present memory effects and how long they are, and what kind of residual error you get for a specific choice of symbol groupings. And now we end up here with these charts that are very colorful, where the top one is a measured one and the bottom one is a simulated one, and every pixel in this chart stands for one group of excitation signal, and the color indicates how well they are going to be predicted by the nonlinear circuit simulation for a specific chosen memory length. And I mean, for the use as an actual model, this would be a rather bad choice, because you can see there are still some black pixels left here. But it's very interesting from an academic point of view, since you can see here that some of the transitions, as we call them, these groups of symbols, showing a longer memory behavior, so have a greater residual error than others do. And these two charts and the similarity of these two charts should just indicate that this lookup table model is really capturing all these effects. So now let's get on how we could simulate this in a practical manner. And first of all, some general words of advice, which I want to clarify later on. If you want to have a simulation using microwave office running in the loop, indexed by MATLAB, then please have a file that is very compact and dedicated for the simulation purpose. Do not have a lot of variety of subcircuits and so on. Use the hierarchical schematics, so reuse as much of the circuits as you can, and use very meaningful names, since we will be indicating all the circuits and the variables by their names, and things get messy if you don't choose them wisely. So for example, if we take this kind of, I would say, generic power amplifier circuit and want to manipulate it in some way to do a kind of optimization run or whatever you want to do, it's basically up to the user. We first of all build the circuit and make it work within microwave office. And I went with a very generic form, so it's got here really just one input and one output. And one would be very tempted to do some kind of this waveform simulations to just put a arbitrary signal source here, plug in a specific waveform, and let the simulator run and so on. But this is not the optimal choice if you want to do also some other analysis like delay estimation where you really need two ports. So I stuck with this very generic form, abstracted it by putting it into another circuit which was called DUT, where, as you hopefully can see here at the top, there is a variable where you specify what you mean exactly by DUT. And by writing here the name of the circuit, you can say, okay, I want to now have this and that. And for doing the waveform analysis, you add a source here, or if you want to do, for example, a delay estimate, you just add a second port. And you can switch a whole lot of different circuits by just replacing that name here. This is just the way I built the arbitrary waveform port here. And if you now let the simulator run, you get these waveforms. Here the blue curve is showing just the output waveform, and the brownish line at the top is indicating the intrinsic voltage waveform at the intrinsic transistor, which was the parameter we were mostly interested in. So this is the way I set up the simulation, and now we want to take it one step further and really incorporate into this simulation cycle, since this has the additional advantage that when we run this MATLAB AWR simulation cycle as many times as we need it to fill up our database, we can then simulate any arbitrary kind of modulation sequence just by having this database. So we only have to fill it once, and this is computationally very efficient. So we wrote a MATLAB class that can access AWR, Microwave Office, and actually I have to talk with Antti about this later on, but actually we would like to share it with you guys. If you're very interested in using it, we would like you to have it. And basically it works like this. When you are starting it up, you're supplying a file name of this dedicated project, and it creates an object, and this is called A here. And this object now comes with quite a variety of commands you can call on that. For example, you could say list schematics, and then it gives you this list of schematics you have present within your project tree, which is a very convenient way of relating them to each other. And then you can do the very same as just clicking on it. You can say activate this kind of schematic. For example, here we activate the source. Or for this other example, we say, okay, now list it, and now activate the schematic DUT. So we are basically in this schematic, and then we say, okay, now list all variables within the schematic, and we get all variables with the current setting they have. And then you have the set variable command, which allows you to plug in numbers, array lists, strings, and whatever. And this is, I would say, a bit more convenient to use arbitrary microwave office files than the way Visual Basic often handles it by just addressing it using numbers, which can be cumbersome, especially when the project gets changed or gets larger. And then you have the simulation command, which is the very same as clicking on the simulation button, and of course addressing the results of the simulation is now something very similar. You also have a list graph command, which results then in the output of all the graphs you have. You just copy and paste the name you want to have, activate this graph, list all the measurements, and then you can see, okay, we have 2 measurements in this graph, and this is the only thing where we have performed a bit more elaborate implementation, since these always are very lengthy names and we are somewhat lazy people. We're using regular expressions here, so you don't have to type in the full name, so you can just use an identifier that is long enough to specify which graph you really want to have, and then you can have only the y data points, the complete list of xy pairs, or you can also get the units if it's for whatever reason important for your software to see if these are voltages over time or whatever. And you can also get the ID of the data set you're reading out. And this is somewhat convenient because you can plot it inside of MATLAB or whatever you like in order to get somewhat convenient, fancy looking graph for whatever applications you might be interested in. And what is, I guess, the more important feature for most of us is you can optimize some iterations for optimizer runs, for example, or for comparing multiple data sets, or whatever you're interested in. As long as you can perform it once inside Microwave Office, you can now do it automatically using this class. For example, here I just made up a list out of the name of the DOTs I want to try and compare them, for example. Then activating this DOT schematic, and here you can see why this hierarchical structure is kind of important, so that you only have a single variable you have to change in order to conduct a multiple of simulations. And then you're plugging in the name of the DOT you want to use for the simulation run the simulation, extract the measurement, plot them, and start all over again till you run out of new candidates for the device under test. And this is what it looks like. Here you can see the dummy DOT, which is basically only a through connection, and two realizations of such a dedicated amplifier in comparison to each other, and the output waveforms. So of course this is just a bit of a toy example and nothing terribly practical, but in the very core essence, this is what makes our lookup table extraction fly. And as I told you before, we really want to provide this kind of information to who's interested. So contact me during the break, or maybe we can find a way to share it in a more prominent manner using you guys from AWR. So we will manage and find a way. Okay, so that's all for me. I was hardly able to stick to the time frame. Thank you very much for your patience.